Hello, this is lecture 6 of chapter 2, Transmission Lines and Wave Equations, a continuation of the going on discussion in the past 5 lectures. This lecture here will be talking about the issues of reflection and standing waves. What's the problem there? Well, we have a few items underneath: power delivery, quality of signal delivery, and then the combined power and signal delivery constraints. And then we'll go into impedance matching and how to achieve it, some of the typical examples that are used in that regard. Now, we start with the chat here. What's the problem with standing waves? Why do we have to have matching? So far, as a result of our appreciation of what's going on here, we understand that transmission lines can either have a pure traveling wave situation where the signals travel in one direction and never come back, and in other situations, part of the signal reflects back from the load and may experience some further reflections due to the source mismatch as well. And in some other situations here, a total reflection happens from the load and we have a pure standing wave. So we can have either pure traveling, pure standing, or a mixed situation. I guess from the title that we have here, the issues of reflection and standing waves, there is an issue. And actually the issue is twofold: power delivery and quality of signal delivery. Now, using simple logic, when a signal reflects back from the load, that means the load didn't get it all. And there is an issue of power not being delivered to the load because some of it came back. On the other hand, from the signal delivery point of view, if a signal bounces back and forth, there will be multiple deliveries of the signal to the load end, and that obviously is going to cause some quality issues. So let's go analytical about this discussion here. We start with power delivery, and from basic simple circuit analysis, I'm sure you've seen this before, how much power is delivered to a load, and you work out this expression here, and you maximize the power to the load, and you discover that the power in the load is maximum only if the reactances in the source and the load cancel each other. In other words, when the impedance of the load is the conjugate of the impedance of the source. And actually, if you recall, if you study that in power, power factor correction is typically the load for residential homes and many other places is inductive, and therefore we try to make the capacitive source here to compensate for the inductive load, and therefore we improve the power transfer here. So that's really what we're talking about here by the conjugate of each other here. The sum of the reactances ideally should be 0. Alright? Now, to apply this finding to a transmission line network, we need to apply this constraint here at both the sending end as well as the receiving end. The sending end here has to see a conjugate match of the input impedance here with the source, and once the signal arrives here, it also requires that it sees a conjugate match between the load impedance and the line delivering the signal here. So applying that at the source end, and this expression tells us that gamma S conjugate must equal to gamma L e to the minus 2 gamma L. While applying the constraint at the load end, we'll discover that gamma S conjugate is equal to gamma L e to the 2 gamma L conjugate. So gamma S conjugate is the same here, gamma L is the same, so this term here must equal to that term, and that's what we're writing here. And for e to the minus 2 gamma L is equal to e to the 2 gamma L conjugate. The J beta meets that constraint, but the here e to the minus 2 alpha L, e to the 2 alpha L, they have to be equal, and that means alpha must equal to 0. So the conclusion is that this should be a lossless line. For these two constraints to be met simultaneously, you must have a lossless line. Once you have a lossless line, then you need to do the conjugate matching as determined by these equations. Next, we discuss the signal delivery in terms of the standing waves, and obviously standing waves are going to cause, like we mentioned earlier, multiple delivery of the signal, and that's distortion. And to make this a bit clearer, we took a simulation here where we had a pulse that traveled down the line. The line is dispersive, so it caused the pulse to spread. If we had a single delivery, we would have received a pulse of this nature. And as a result of the multiple reflection, we are seeing a portion of the first pulse coming through, and then multiple reflection will take place, another reflection, and as you can see, quite a bit of distortion here as a result of that. So it's obvious that we have distortion as a result of multiple reflection, and the remedy to maintain signal integrity and signal quality is to have 0 for both gamma S and gamma L. You can't have a reflection at either place. And as a result, you can write those expressions, and here is the constraint that we have: gamma S is equal to gamma L is equal to 0. That reduces the voltage at the load to be equal to half of the voltage at the source, e to the minus gamma L. And here's further analysis of the constraints that we wrote earlier. Here, if we have gamma sub S is equal to 0 by itself, or gamma sub L is equal to 0 by itself, or if we have both of them equal to 0. Now next we discuss the combined power and signal delivery constraints. What if I'd like to get maximum power at the same time a clean signal delivery with no integrity issues? Well, the discussion that we had earlier is telling us that both gamma S and gamma L have to be 0, and our line must be lossless or near lossless. In practical situations, we can never achieve that. We can get close, but there will always be an element of loss, and there will always be some mismatch. Matching wise, we need to do something about that. If we cannot make both gamma sub S and gamma sub L to be 0, we try to reduce the mismatch to a minimum.